NASA's Artemis 3 mission is designed to put humans back on the lunar surface, specifically targeting the South Pole for sustained long-term operations. During the Apollo era, the engineering solution was monolithic. A single Saturn V rocket carried every piece of hardware required for the entire mission. But the mass fraction math changes when you need to sustain a crew for weeks. Carrying a heavy surface habitat all the way from Earth makes a single launch vehicle highly inefficient. To solve this, aerospace engineers shifted to a distributed mission architecture. Instead of one massive rocket doing everything, the workload is divided across multiple specialized spacecraft. Deep space transit from Earth to the Moon is completely decoupled from lunar descent and surface habitation. Under this model, NASA's Space Launch System and Orion Command Module handle the transit, while the SpaceX Starship Human Landing System, or HLS, handles the descent. This requires the massive Starship HLS to be fully launched and pre-deployed into lunar orbit before the human crew even leaves Earth. Decoupling these transport systems is the only mathematically viable way to place and sustain heavy human infrastructure at the extreme environment of the lunar South Pole. The human journey begins here, with the Space Launch System fully stacked and preparing for launch on Earth. The SLS has a single initial objective: generate enough raw thrust to push through the dense lower atmosphere and achieve Earth orbit. This schematic plots the rocket's flight path. The first critical event occurs 2 minutes and 10 seconds after liftoff. At 45 kilometers in altitude, the two solid rocket boosters deplete their fuel and detach from the core. The core stage burns for 6 more minutes, reaching the next staging event at T plus 8 minutes 30 seconds. At 160 kilometers up, the liquid hydrogen core stage separates. Orion is now officially in Earth orbit. What remains is Orion and its attached upper stage engine, known as the Interim Cryogenic Propulsion Stage, or ICPS. Looking at this orbital map, we see the ICPS execute the translunar injection maneuver. The engine fires, providing the thrust required to push the Orion spacecraft completely out of Earth's gravity. This precise injection burn commits the Orion capsule to a 4-day deep space transit toward the Moon. The entire purpose of the massive SLS rocket is simply to impart enough delta-V to put the tiny Orion capsule on an intercept course. After its 4-day journey, the Orion spacecraft arrives and stabilizes its orbit in cislunar space. Waiting patiently for it in the dark lunar vacuum is the massive pre-deployed SpaceX Starship Human Landing System. This initiates the most critical logistical phase of the mission, the Lunar Orbit Rendezvous. This orbital map demonstrates the precision docking procedure required to link Orion and the Starship HLS while traveling thousands of miles per hour. Once sealed, 2 astronauts transfer out of Orion and step into the massive Starship vehicle. The remaining 2 astronauts stay behind. Their job is to pilot and maintain the Orion Command Module in orbit for the duration of the surface mission. With the payload and crew transfers complete, the Starship HLS physically undocks and begins calculating its descent vector. This mid-orbit swap allows the landing crew to descend while leaving their heavy Earth return heat shields and deep space fuel safely parked in orbit. The Starship HLS drops out of orbit, firing its engines to control its descent. Its target is the deeply shadowed lunar South Pole. This specific topography is strategically valuable because these permanently shadowed craters hold high concentrations of raw water ice. Nearing the surface, Starship deploys its 3 distinct landing legs and touches down. This cross-section reveals how Starship differs from historical landers. It operates as a multi-story integrated habitat, towering so high above the surface that astronauts require an external elevator to step onto the lunar soil. The crew will rely on these internal systems for a full 6 to 7 days of continuous surface operations. Their scientific payloads include advanced seismometers, deployed to measure deep lunar tectonic activity. They will also drill for physical water ice samples, testing the viability of local resource extraction for future deep space fuel. The daily operational loop requires the astronauts to retreat up the elevator into the Starship module each night, utilizing its secure life support systems for sleep and data analysis. In this capacity, the Starship HLS acts as the first true operational prototype for a stationary, multi-day off-world base. To return home, the Starship HLS fires its engines directly from the South Pole, ascending to match orbits with Orion. During a second lunar orbit rendezvous, the landing crew and their geological samples transfer safely back into the Orion spacecraft. The Starship HLS is then abandoned in lunar orbit indefinitely. Engineered exclusively for vacuum operations, it is completely incapable of surviving Earth re-entry. Orion immediately initiates its Earth return burn, committing the crew to the multi-day transit back. Approaching Earth, the crew prepares for atmospheric re-entry, jettisoning the aft service module. Hitting the atmosphere translates immense velocity into intense kinetic energy, forcing Orion to rely entirely on its thermal heat shield to survive the friction. This scale tracks Orion's descent altitude against its velocity, outlining the precise aerodynamic deceleration sequence required to arrest its fall. At exactly 25,000 feet, or 7.6 kilometers, 2 drogue parachutes violently deploy to stabilize the tumbling capsule. Descending to 18,000 feet, or 5.5 kilometers, the 3 massive main parachutes deploy, catching the thick lower air for final deceleration. Precise mechanical staging in the thick atmosphere ensures the capsule reaches terminal velocity, resulting in a safe ocean splashdown. This split-screen graphic compares the immense gravity well of Earth against the much shallower gravity well of the Moon, highlighting the final resting places of our hardware. The Artemis III architecture works strictly because it assigns highly specialized vehicles to specific gravity wells. Orion recovers in the Pacific Ocean because it is built to handle the extreme high-energy demands of Earth escape and atmospheric friction. Starship HLS remains in orbit around the Moon because it is optimized purely for the cold lunar vacuum, unburdened by heavy aerodynamic requirements. This distributed, multi-vehicle architecture allows us to explore the lunar South Pole, but more importantly, it provides the exact mechanical framework required to safely launch human beings to Mars.